We have a question from GATE 2023, question number 38, and C0, let C00 be the space of all those sequences such that xi is not equal to 0 only for finitely many indices. Like for example, let's consider 1, 2, 3, and then 0, 0, 0. All are zeros. So it has non-zero, only finite elements are non-zero, otherwise all are zero. So this is C00 is set of all such functions, set of all such sequences having only finitely many non-zero, and all others are zero. All elements are zero. And we defined a norm on this x1, x2, x3, the sequence infinity norm, which is also called sup norm. We just take supremum of all the absolute values of the elements. Then we define two functions f comma g from the same space to the same space, and it is defined as the value of function at any sequence x1, xn is just simply we are multiplying with this sequence each term. And similarly in G we just multiply by this sequence, 1 upon this sequence at each term. So we have a question is f is a continuous, but G is simply we need to check if f or G are continuous or not. First of all, check, it is very easy to check that f and G are linear function. Okay, you can check this. And now there's a theorem which says that a linear function from a norm space to a norm space is continuous if and only if it is bounded. So we need to show that so if T is continuous if and only if T is a bounded linear operator, which is we need to show that Tx norm is less than equal to some k times x for all x belongs to x. This is the definition of bounded linear operator. So according to this, we only need to check that is f and g are bounded. To tell the continuity, we need to check if f and g are bounded or not. Okay, we will show that f is not bounded. F is not bounded. Just let me write again. F was defined as 1 plus 1 x2 so on n plus 1 by n xn. Okay, to show f is not bounded, we will show that for any k belongs to R plus positive real number, we have f x norm. There exists some sk belongs to C00 says that fxk norm is greater than equal to k times xk norm. Just see, this is a condition for boundedness. To show it is not bounded, we are not able to find the k. For this is possible for every real number we choose, we can find some k xk, which is makes it, we change the inequality. Inequality does not satisfy. Okay, so we will show this. Now, first of all, see that n plus 1 by n tends to infinity as n tends to infinity. Okay, thus for n k belongs to R plus, there exists some mk belongs to natural number such that mk plus 1 by mk is greater than k. Okay, alright. So now we define xk. We need to show we need to find this sk. Now we will define how this sk is. The sk is 0 0 0 and just 1 on this mkth place. This is a natural number. It is 1 at mkth place. This is how sk is defined. Now what is fxk? Is a c. Okay, let's use another notation so that it is not confusing. This is how we define the xkth sequence. So xk norm, this is equal to, you can simply check everyone else it is 0, only here it will be multiplied, so it will be equal to mk plus 1 by mk, which is greater than k, and this is equal to k times xk infinity norm. What is its infinity norm? It's supremum of all the elements. There is only one non-zero element, so xk infinity norm is simply 1. See, the definition of x1 x2 x infinity is a supremum of all. They all are 0 or only 1, so it is very easy to see that this is only 1. So now, so we have shown that fxk infinity norm is greater than k times xk infinity norm for any k belongs to R plus. Thus f is not bounded, which implies f is not continuous. So at least we know that f is not continuous. Now we will show that G is bounded. G is bounded operator. Recall that G was defined as xn 1 by 1 plus 1 comma x2 2 plus 1 by 2, and so on x n plus 1 by n, and so on. So now g x1 x2 xn norm is equal to x1 1 plus 1 by 1 infinity norm, x2 2 plus 1 by 2, and so on xn n plus 1 by n infinity norm. And okay, let's see that for any xk, xn is less than x, this is more or less, xm is less than x infinity, oh sorry, this is true because this is this is the supreme of all the xm, m belongs to natural number, so any m, this is also true. And now so just consider any element xn by n plus 1 by n, this is, and we just take its modulus. This is equal to xn modulus by 1 by n plus 1 by n. Okay, so this sequence is bounded. We know that this sequence converges to 0, this must be bounded, and I think it is bounded by 1 by 2. Yes, you can check this, you can verify. Verify 1 by n plus 1 by n is less than 1 by 2 equal to or not. It's an easy task, you can see that. Whatever, it doesn't matter whatever it's come, but it is upper bounded, that is more important. So this is less than equal to x1 x2 x infinity times 1 by 2, because this term is less than 1 by 2 and this is less than this norm from this previous slide, from here using this. Thus this is true for all n belongs to natural number. Hence x1 1 plus 1 by 1 norm xn n plus 1 by n so on norm infinity is less than equal to x1 x2 xn infinity times 1 by 2. Thus g x1 x2 norm is less than equal to 1 by 2 x1 x2 infinity norm. Hence g is a bounded linear operator, which implies g is continuous. Thus f is not continuous by g, b is the correct option.